Hey everyone, welcome back to another explainer. So, have you ever wondered exactly how a first-order system reacts when it's hit with an almost instantaneous input? Kind of like striking a massive gong with a mallet or your car's suspension just violently slamming into a pothole? Well, the answer to that lies in something we call the impulse response. It's an absolutely crucial concept because it perfectly reveals a system's natural, totally unforced dynamics. It literally lays bare the initial amplitude and that intrinsic rate of decay, right before any continuous external forces can step in and interfere.
How does a system react instantly? Well, let's dive right in. We're continuing our broader series on dynamic systems, and honestly, this exact question is the foundational building block for, well, pretty much everything that follows. We're going to explore this by looking strictly at instantaneous inputs. We're essentially just stripping away all the noise to see the raw, underlying mathematical behavior of a first-order system.
To wrap our heads around this, we use this really beautiful mathematical concept called the Dirac delta function. Think of it as an insanely intense input, all packed into exactly one singular instant, right at time zero. It's basically theoretical perfection. But, the real magic happens when we apply the Laplace transform. It totally shifts our perspective, and the math suddenly becomes incredibly elegant. Get this, the transform of that wildly complex, concentrated impulse is simply the number one.
And that simplicity, it's a massive cheat code for our calculations. Normally, to figure out our output, we have to multiply the transfer function by the input. But since our input here is literally just the number 1, all that extra math just vanishes. For a first-order system, the output profile is completely unmasked. It's 100% dictated by its own transfer function. It's like the system is just talking directly to us, completely unprompted.
But, hey, we don't actually live in the Laplace domain, right? We live in the real world. So to see what this actually looks like physically, we've got to transition back to the time domain. By applying the inverse Laplace transform, this equation just beautifully unravels into the standard formula for exponential decay.
Let's take a second to look at what this actually means for a physical machine. There are basically two key parameters pulling the strings behind the scenes here. First up is K, the system gain. Now, K dictates the sheer size or amplitude of the reaction. And then there's the Greek letter tau, which is our time constant. You can think of tau as the system's internal clock. A positive time constant absolutely guarantees that this sudden burst of energy is going to naturally bleed away over time, giving us a stable, decaying response. It's fascinating to think about how this math plays out in practice. Immediately after that unit impulse hits at time zero, the response doesn't gradually ramp up. No way. It basically instantly teleports to its initial value. That peak, which is k divided by tau, is the absolute maximum value the system hits. It's like the system takes a hit and bam, it wakes up right at its absolute limit.
But of course, it can't sustain that kind of energy. The instant after the impulse occurs, the mathematical slope is severely negative. The system is just desperately trying to dissipate all that energy it just swallowed. It points straight down a trajectory that, really neatly, aims for the time axis at exactly our time constant, tau.
And this is exactly where tau acts as the ultimate master dial for your system. If you've got a really tiny tau, well, think of it like a highly strung sports car suspension. Your initial spike is super violent, but the energy decays incredibly fast. On the flip side, a massive tau is more like one of those heavy, sluggish door closers. The initial jolt is much smaller, sure, but it takes an absolute eternity to bleed off that energy.
But ultimately, the math always wins. Whether your time constant is a tiny fraction of a second or a full hour, the curve is inevitably going to approach zero. So the golden rule to take away from this explainer today is this. A first-order impulse response is always an exponential decay. It's born from an instantaneous initial value, and its lifespan is dictated entirely by its time constant, tau.
Which brings us to a really fascinating threshold. If a single split-second impulse causes such a dramatic, decaying reaction, how on earth do these exact same systems survive a continuous, relentless input? Something like a sustained force or a ramping voltage. Well, we are going to be uncovering exactly that in the next explainer in our Dynamic Systems series. But until then, I want you to ask yourself, in the engineering systems you rely on every single day, is a fast time constant a feature or is it a fatal flaw? Think about it. If this explainer helped you master these concepts, be sure to like, subscribe, and share your thoughts below. See you next time.